everyone, welcome to this explainer. Right now, literally as you're sitting there, there is a massive, highly calculated, but completely invisible infrastructure operating directly above your head. It's powering our internet, guiding our maps, predicting the weather, and of course, keeping a close eye on our changing climate. But these machines aren't just tossed up into the sky at random. No way. They exist in meticulously designed pathways. So today, we're decoding satellite orbits. Let's uncover exactly how this invisible choreography actually works. It brings up a really fundamental question, doesn't it? Why are all satellites just in the exact same orbit? It's kind of tempting to think of space as this single vast highway where everything just floats around at the same height. But space is entirely three-dimensional. Putting every single satellite into the exact same orbit would literally be like forcing every type of vehicle, from a tiny bicycle to a massive freight train, into the exact same lane on the freeway. It just wouldn't work. To really grasp how this all fits together, we need a good mental model. So think of satellites like photographers trying to capture the absolute perfect shot. Every orbit is simply a different type of photographer trying to achieve a highly specific goal. Some of them need to be right up in the action, some need to see the entire crowd from afar, and others just need to stand perfectly still and film a time-lapse. Keep this metaphor in mind, because it's going to perfectly unlock the logic behind everything we look at today. All right, here is our game plan for today. First, we'll look at the satellite trade-off. Second, up close with LEO and SSO. Third, the middle ground with MEO. Fourth, the big picture with GEO. Fifth, the polar extremes in HEO. And finally, matching missions to orbits. Let's jump in. Section 1, the satellite trade-off, balancing the factors. Let's dive right into this and define the absolute rules of the orbital game. Because in space, you absolutely cannot have it all. The fundamental reality of aerospace engineering is, well, compromise. There is no such thing as a single best orbit. Every single time an engineer places a satellite in space, they are playing a really delicate game of give and take. If you want incredible high-resolution images, you got to sacrifice broad coverage. Want to see a whole hemisphere at once? You have to accept higher latency or communication delay because that signal literally has further to travel. You're constantly balancing altitude, coverage, revisit time, latency, resolution, and of course the fuel required to actually get there and stay there. Section 2. Up close with LEO and SSO, our closest orbits. Let's move down to our lowest altitude and see how being close to Earth builds the foundation for some of our most critical missions. 90 minutes. That is how incredibly fast a satellite in low Earth orbit, or LEO, can complete an entire trip around our planet. To pull that off, these satellites are zipping through space at a blistering 7.8 kilometers per second. If you've ever looked up just after sunset and seen a bright little dot steadily gliding across the stars, you are almost certainly looking at a LEO satellite hustling through its 90 to 130-minute lap. So, in our metaphor, LEO is the close-up photographer. They are right at the edge of the stage, walking super close to the action, at an altitude of just 160 to 2,000 kilometers. The pros here, you get exceptionally sharp, high-resolution pictures and extremely low signal delay. That low latency is exactly why internet constellations like Starlink use LEO. Your data just doesn't have far to travel. But the cons are pretty significant. Because you're so close, your camera lens can only see a tiny little patch of the Earth at any given time. If you want continuous global coverage, you can't just launch one satellite. You need a massive constellation of hundreds or even thousands of them to ensure one is always overhead. Oh, and this is also the orbit of the International Space Station and those smaller scientific CubeSats. Now, tucked right inside that low Earth band, we have a very special variation called Sun-Synchronous Orbit, or SSO. Think of this one as the time-lapse photographer. Sitting between 500 and 800 kilometers up, this orbit slowly rotates so that the satellite crosses over a specific location at the exact same local solar time every single day, say always at exactly 10:30 a.m. This brilliantly solves a massive scientific problem, which is lighting. By passing over at the same time every day, the shadows and lighting conditions remain perfectly consistent. This makes it incredibly easy to compare images over months or years without being tricked by different sun angles. It is absolutely the ultimate tool for climate monitoring, tracking land use changes, mapping bushfires, or watching sea ice melt over time. Section 3, the middle ground, MEO, balancing view and detail. But what if we need to see a much larger area without losing stable geometry? Well, that's where we step back from the action. If LEO is right on the edge of the stage, medium Earth orbit, or MEO, is the photographer stepping back and standing on a high hill. You're definitely sacrificing that razor-sharp detail of the close-up, but in return, you get a much wider, more reliable view of the entire landscape. MEO operates right around the 20,000-kilometer mark. This is basically the realm of global navigation. Whether you're using American GPS, European Galileo, or other systems like Beidou or GLONASS, they are all hanging out right here. And why is that? Well, imagine if GPS satellites were way down in LEO. They would be whipping across the sky way too quickly to maintain a stable lock on your phone, and we would need hundreds and hundreds of them just to ensure you always had line of sight to at least 4 of them. By pushing them out to 20,000 kilometers, MEO gives us the perfect middle ground. We get wider coverage, far fewer satellites are required, and we get the highly stable geometry needed to calculate your exact position down to the meter. Section 4. The big picture with GEO, continuous coverage. Now, what if our problem requires us to monitor a whole continent continuously, without the satellite ever appearing to move at all? To do that, you have to push way out to a very specific, almost magical altitude, exactly 35,786 kilometers. Welcome to Geostationary Orbit, or GEO. This is our helicopter photographer. Because of that exact 35,786-kilometer altitude, the satellite's orbital period is exactly 24 hours. It perfectly matches the rotation of the Earth. So to someone standing on the ground, a GEO satellite appears completely motionless in the sky. It just hovers over one single point on the equator forever. And this is absolutely crucial for continuous coverage. When you point your satellite dish at the sky for TV broadcasting, you really don't want to have to move it every 90 minutes tracking a LEO satellite. You want to point it once at a GEO satellite and you're done. It's also exactly how emergency services continuously monitor severe weather, like cyclones. They get an unblinking 24/7 eye on the exact same region. Let's put these two extremes side by side to really look at the trade-offs we talked about earlier. LEO gives you low delay and high-res images, but you only see a tiny slice of Earth. GEO, on the other hand, gives you a massive, continuous view of an entire continent, but because it is so incredibly far away, the resolution is lower and you face a communication delay, or latency, of about 240 milliseconds one way. Now, that delay is totally fine for a TV broadcast, but it would be absolutely terrible for a fast-paced video game or a real-time Zoom call. That's exactly why your internet is moving to LEO, while your broadcast TV stays firmly in GEO. Section 5. The Polar Extremes, GEO. Viewing the poles. But there is a bit of a catch here. Because GEO satellites have to orbit directly above the equator to match Earth's rotation, they have a massive blind spot near the North and South poles. Which leads us to our strangest orbit, Highly Elliptical Orbit, or HEO. This is the polar photographer. Unlike the nice, neat circular paths we've looked at so far, HEO is a stretched-out, long ellipse. Thanks to the quirks of orbital mechanics, a satellite moves much slower when it's farther away from Earth. So engineers actually stretch the orbit out so the far end lingers high above the extreme northern or southern latitudes. The satellite zips super quickly past the equator and then spends hours basically just hanging out over the Arctic or Antarctic, capturing exactly what those GEO satellites cannot see. It is a brilliant hack for polar communications and deep space science. Section 6. Matching missions to orbits. Choosing the right path. Let's synthesize all this data we've just gone through. Everything we've covered proves that you don't just launch a satellite, you engineer its perfect environment. This beautifully summarizes the entire architecture of near-Earth space. If your mission is high-res imaging, you absolutely need LEO or SSO because you must be close to the Earth. If you're doing long-term climate monitoring, well, SSO is mandatory because you need that consistent, reliable lighting to compare images over decades. For GPS, you need MEO for large coverage and unshakable stability. If you want to blanket the Earth in low-latency global broadband, you are forced into LEO, which means you have to accept building thousands of satellites. But if you just want to beam a television signal or monitor a hurricane continuously, you want the stationary stability of GEO. The problem always dictates the orbital solution. It completely changes how you look up, doesn't it? The night sky isn't just some empty void. It is a meticulously organized, multi-layered machine working constantly to keep our modern world functioning. So the next time you step outside, look up at the stars and spot a satellite gliding silently in the dark, ask yourself, which invisible photographer is looking back at you? Are they up close catching the action in LEO, standing on a hill in MEO, hovering endlessly in GEO, or lingering over the poles? Thank you so much for joining me for this explainer, and keep looking up.